Welcome to the latest Kielder Observatory podcast then. Heading into July and waving goodbye to June, we're in the mid-part of the year, which means, of course, the nights are a little lighter than they ordinarily would be most of the year, which can make for difficult astronomy, but there's plenty to be seeing in the night sky, and there's plenty going on deeper into space as well. And we're going to be looking at the life cycle of stars and having a look at how stars are born and what happens to them when they die, and how we might be discovering some brand new stars that are deep into space. Anyway, we'll talk more about that and the sheer scale of stars as well with Director of Astronomy at Kielder Observatory, Dan Pye, who joins us now. Hello, Dan.
Hello there. I'm today wearing a very appropriate t-shirt, actually. It's about the existence of state and matter and how when you don't observe things, they don't exist, and all that kind of stuff, yeah.
Yeah, it's certainly true for my bank account. So, sight and out of mind and all that. Let's, before we get on to what we're going to talk about with regards to stars and so on, let's have a look at the things that have been happening at Kielder, because over the last few weeks, you've been doing something a little bit different, haven't you? You've had a bit of a comedy night, some comedy festival, comedy under the stars with stars. You've been watching some movies under the stars and all sorts of different things. Yeah,
it was great. It was nice. We had some comedians up from a group of comedians called Felton Out, who are local-based comedians who've grouped together just after lockdown to get out and about on the scene and support each other in getting back into gigs and such. So it was great to welcome them to the observatory. It was definitely something different, something unexpected, I guess, as well. It was a nice night, though. We had a great time. We had pizza, lots of pizza, and we also had mocktails as well. Then the following night to that, we showed the film Contact, which was the 1997 hit by Matthew McConaughey and Jodie Foster, and written by Carl Sagan and his wife. Of course, the legendary astronomer that was Carl Sagan, he kept all of the science as accurate as it was for the time, and the film was released actually after he died in 1997. And what's interesting about it is it centres around a star called Vega, and Vega is a beautiful big bright star in the constellation of Lyra, visible right now. And it's a lovely big bright star, you can see it in the sky. It's 25 light years away, and it's 25 years since that film came out. So if anybody did send a little message at the speed of light from Lyra, from Vega, when that film came out, we'd just be receiving it today. Isn't that nice?
There you go, you see. And then you went outside and had a look at it for yourselves in the night sky.
Yeah,
and as you say, it's one of the brightest stars in the sky at the moment, isn't it? And regularly, actually, through the course of when it's visible. It's one of the most obvious ones and the first ones that maybe you notice when you look up.
It is. It's our zero magnitude star. So that's what we kind of measure all of the magnitude of the other stars from, is this one. Well, it's interesting with magnitude, and I don't want to kind of delve into it too much because it gets a little bit wordy and all logarithmic and such, and who wants to do maths on a podcast? But anyway, it's actually I think it's something like 0.0054 of a magnitude or something. I'm not entirely sure how we get points of magnitude to such a degree nowadays, but hey-ho, here we are in the world of technology.
So, that's the one that all stars are judged by, and we're going to talk more about stars very soon because we're having the news at the moment, stars dying off, other stars being discovered, and how we go about understanding the process of stars, the life cycle of a star, and also to get some of the scale of these stars that we look at from Earth, and we look up to the night sky, and we see the stars that we've just been talking about there. But obviously, if you were to get quite up close to them, these would be absolutely massive balls of fire. So we'll talk about that more in just a moment. As we head into July, Dan, what's on the agenda at Kielder Observatory, and what are sort of the things that people should be looking for in the night sky as well, wherever they may be?
We're moving into our summer schedule, isn't that nice? So this is the schedule where it's dominated quite heavily by all of the kids' activities, which start from the 20th of July. And through the 6 weeks holidays, we'll be running more kids events. Still loads of availability through August as well, actually, so plenty of opportunity to book onto all range of events. And actually, from mid-August is when we start to get our really good dark skies back as well, so a great time to come and visit. Arguably, I would say that from mid-August to maybe the beginning of October is my favourite time of year to do stargazing. And it's because we start to get some great features back in our sky. The planets are coming back into the sky. They're getting earlier and earlier and earlier. You can see Saturn rising from about midnight now, and Jupiter not long after that. And then as we start to get into the early hours of the morning, we've got Mars, we've got Mercury, we've got Uranus and Neptune's hanging around in there. So all the planets are kind of coming back into our skies as we start to move around into August again. And like I say, that'll get earlier and earlier and earlier as the months progress. And they are certainly some of the most interesting objects to look at with a telescope. We've also got some great moons on the way as well. We've got the biggest supermoon of the year, as interestingly named as we now call them, supermoons. Anything that's kind of out of the ordinary, I just think should have that title to it. Supernova, supermoon, super sun. That should be it during the summertime. Or something, I don't know. So all of these things happening as we progress through July. July is, of course, one of our lightest months here in the Northern Hemisphere. At 55 degrees, we can't really escape that. That's just how science works. We're on a tilt. If you have any complaints, take it up with the Earth's axial tilt. It's their fault. Or if you want to do some really hardcore stargazing at this time of the year, then you need to go a little bit further south. So we'd be heading to places like southern Spain, parts of Africa, La Palma, Tenerife, places like that. Great time of year to go stargazing there right now. And in fact, actually, our director of astrophotography, director of astronomy is me. That was wishful thinking. Is actually in La Palma right now, taking some pictures on a volcano without me. And I'm really bitter and just enraged about it, really. So I hope the volcano goes off while he's there and it ruins all of his photographs. Anyway.
Nothing like a bit of vengeance there. Dampai willing a volcano to erupt on one of his colleagues. It's quite outstanding. So there's a few things. You touched on the kids sessions there. There are a number of different kids sessions. Just run us through the different things that are happening for anybody listening to this who's looking for ideas for over the school holidays, because of course they got underway the end of July, running through August into the first week of September. So there's availability there. But if people want to pop up to these sessions, they don't happen late at night, do they? These happen late on in the afternoon, so people can pop along. It's not particularly, too late for bedtime and all that kind of stuff. And you can still, even though it's daylight, there's still things you can do. Yeah, there is. And there's two events that we run through the summertime. The two Space Kids events that we now run are Solar Quest and Rockets and More. So Rockets and More is launching rockets, building rockets, looking through the telescopes, of course, if it's clear, and learning about rocket mechanics briefly, and all sorts of other activities that we do through the kids throughout those events. The second one, Solar Quest, is all centred around looking at the sun. So with that, we can use our radio telescope to take an image of the sun throughout the event. If it's up, which it should be at that time of year, yes, it is, yes. And also, we will be looking at light and deconstructing light and figuring out what light is and how it tells us more about our place in the universe as well, with some really cool little activities. You get to take home this little solar bracelet, which changes colour in sunshine, and we teach you about all of that as well. So those are the two kids events for this year: Solar Quest and Rockets and More. Yeah, so get yourself down to any of those if you can. Get on and book, because they're great events for the kids. And we did a podcast about a year, I think, or so ago. So go back in the back catalogue and you can actually hear what happens at one of those events with the kids letting off their rockets with varying degrees of success. But it's all good fun. So check out those sessions and be part of them if you can. Let's get on to our main topic for this particular episode then, and we want to give you an understanding of stars, really, because it's something that I know that we're an astronomy podcast and we have mentioned stars. We haven't really talked about what a star is and the sheer scale that these stars can reach elsewhere in the universe. Obviously, our star that we know the best is the one that shines down on us most days, which is the sun. let's just start with the sun as a reference point, because people can relate to that. We know how big that appears in our night sky and what it feels like, of course, and you might be sweating your faces off under it listening to this, or you might be having to wrap up warm. Obviously, we're in a very particular place in the universe here on Earth and in this particular country, and it affects us greatly. But using the sun as a reference point, which is our closest star, it's a star that we've all seen at some point. And we know roughly how big it is, but the sun is not the biggest star in the sky by any stretch of the imagination. Let's talk about Vega, which is a star that we mentioned a little while ago, one of the brightest ones in our night sky. How does that compare with the sun? If you're to put them side by side, which I realise astronomically and even with the laws of physics is a very difficult thing to do, but if you were to compare them side by side, how big is Vega, and how does it compare with the sun? Well,
you could get them close to each other. You could put them in orbit around each other and kind of measure them off each other that way, but they'd still be really far away. So the Vega is more than double the size of our sun. Our sun's just a little under 1 million miles in diameter, whereas Vega is close to 3.3 million kilometres in diameter. So it's much, much bigger than our sun, more than double the diameter, which means that you could fit a lot of suns inside of Vega, and I can't work out off the top of my head what that would be, but you can fit, in terms of our sun, you could fit the Earth inside of our sun 1.3 million times. So just to kind of put it in context, that's how big the sun is, 1.3 million times the volume of our little Earth. And the Earth feels massive to us, of course, but then Vega is more than double the width of our suns, and you'll be able to fit quite a few suns inside of Vega. So imagine how many Earths you could fit inside of Vega. It's a huge, 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 huge star. Massive star. In fact, actually, let's have a think. We might be able to work out how many Earths across we could do. Yeah, probably more than 200, up to about 250 times the diameter of our Earth would be the size of Vega. So it's quite a substantial size.
Yeah, it certainly is. And how does that, though, compare with the biggest star that we're aware of so far in the universe? Because I'm sure that's big. That's obviously a lot bigger than our sun. But how does that massive star compare to the biggest that we know?
The biggest star in the universe that we've been able to really spot so far has actually recently changed. It's something that has come onto the scene fairly recently. I can't remember when it was, but it was a fairly recent candidate. It's called Stephenson 218, and we think that is absolutely ginormous. So we're talking about maybe 2,150 times the radius of our sun. So it's an absolutely ginormous object. Huge object. Put that into kind of context. The orbit of Saturn sits around 2,000 times the radius of our sun. So this is huge, massive star that if you put it inside of our solar system would come out as far as beyond the orbits of Saturn, which is just astonishing to think about. And that's really interesting because when we look at stars, we think, based off our current knowledge, that the maximum size that you could possibly get to, particularly in the Milky Way, is 1,500 times the radius of our sun. So 1,500 times 700,000 kilometres. And there is actually a star which we have observed which is a little bit bigger than that, which is UI Scuti. It's the biggest star in the universe, as we understand it just at the moment, and that other than Stephenson, which is still, I think, debated is Stephenson. But usually UI Scuti is the one that people would reference as being the biggest. And that one is 1,700 times the radius of the sun. So bigger than our theoretical size limit of the Milky Way.
Wow. That is big. And there's stories that people may have read recently about another star, Canis Majoris, which is a very, very big star, of course, as things go. But that's a star that's on its way out at the moment. It's slowly dying. And this has been observed for a little while. But just to talk about the life cycle of a star, and in a moment we'll talk about perhaps a new star that's been discovered, because they don't come along too often, of course. But for a star that's on its way out, it's quite a spectacular process, isn't it? As a star sort of melts down into itself. Just talk us through that process.
Yeah, and we talk about Canis Majoris in this case being dying very, very slowly, but in astronomical terms, it's happening very, very quickly. If you think again, comparing this against our sun that we have, our sun's 4.6 billion years old, somewhere in that region. Whereas Canis Majoris is a little over 8 million years old. So it is a much, much, much younger star, but it's dying much, much quicker than what our sun is. And it's probably only got a very narrow window of life left, maybe into the hundreds of thousands of years, maybe even less than that. So it's not going to last a very long time at all, and that is because of its size. It's ginormous. The general kind of life of a star all begins within what we may call a nebulae or a nebula, a big cloud of gas, and within that cloud of gas you've got lots and lots and lots of hydrogen, huge amounts of hydrogen, which is clumped together, because we talk about hydrogen being the most abundant thing in the universe. There is lots of it absolutely everywhere, but occasionally we'll happen across these big clouds of hydrogen which have found their way towards one another through gravity. And within these clouds, if we leave them alone and do nothing with them, they'll just sit cold, and that makes them very difficult to see. But if they're stimulated to activate star formation, that's when we start to get stars. And that all happens with usually a gravitational disturbance that's happened somewhere else in the galaxy. So somewhere else in the galaxy, a star, for example, might explode, and that sends this huge gravitational ripple through our galaxy. That gravitational ripple excites all the hydrogen within this big cloud of stuff, and then it triggers stellar formation, which sounds like it's a really easy process when we put it like that, but actually it's a very difficult process, because what we're trying to do with stellar formation, and this is the difference between, if you were to look at the two objects, a planet and a star, and I fully appreciate that many people come to the observatory and aren't really aware of what a star is. And sometimes I'll get to the end of an event and somebody goes, that was amazing. But what is a star, and why is it different to a planet? So just to kind of give you the defining principles between the two. A star occupies the centre of a solar system, and it comes from a big cloud of hydrogen which has started to fuse. So you might call it a hydrogen fusion engine. That's what a sun is, or a star is. And then planets, they form around stars, usually because of the leftover debris from the formation of the star, and that's what creates the planets. Now, the fusion process that starts a star is a very difficult process to start going, because if you want to try and fuse hydrogen together, which is the thing that gets this process going, and hydrogen is number one on the periodic table. It's the most basic of element. And for those of you who aren't sure what fusion is, its overarching term really is to take elements and put them together to create a heavier element. And in this case, what we're doing is we're getting hydrogen, sticking it together to create helium, which sounds really easy again, but that's not that easy either, because if you get hydrogen atoms all very close to each other, they don't want to interact with each other. They want to bounce away from each other. It's like trying to stick the opposing ends of a bar magnet together. They'll just springboard away from each other all of the time. But given those special circumstances, if you really force them together, using gravity as the thing that stimulates them, then you end up with little hydrogen atoms interacting with each other. And when they do, when they join together, that's what creates helium through a series of somewhat complex reactions. It doesn't go hydrogen, helium straight away. It'll go hydrogen, deuterium and tritium, and then helium. But we just kind of skip out the deuterium and tritium bit when we're talking about it in greater detail. So we go from hydrogen to helium. And that's what starts the evolution of a star. Now, if you get a lot of that, it's quite a self-contained system. It can continue. It can get out of hand almost. And then these objects, as they gravitate towards each other, they'll constantly keep themselves under gravitational pressure. So all of that gravitational pressure continues the process of hydrogen fusion in its core going. That puffs the star out like a balloon. But then because the star is so big, it's held together through gravity in this balanced state that we call it. We've got a fancy term for it. We use this in planetary sciences as well. We call it hydrostatic equilibrium, where the outward force and the inward force is kind of equally matched, which is what keeps it in that lovely spherical shape. And then there we go. You have a baby star. Congratulations. It's a star of neutral gender.
Of course. So that's how they're formed. I guess maybe the question that many people will have is with regards our own nearest cousin, our nearest star being the sun. In theory, this is not going to take place for a great amount of time yet, and it's probably not something that we should be particularly worried about. But our own sun eventually will start to run out of steam. When do you think that will be, and how do you see it all ending for the solar system with that in mind? Because it's going to be quite dramatic, isn't it?
Kind of less so dramatic than many other stars, because our sun isn't very big. I mean, it is to us, but in the universe, it's a fairly small star. If we got 60 light years away from our sun, we wouldn't really be able to see it. And considering that many of the stars that we see in our night sky are beyond 60 light years, I think that really puts into context just how small our sun really is. It's a very, very small sun. Its gradual death will begin potentially in the next 4.7 to 5 billion years. And when it reaches that point, that's when it'll eventually start to increase into its red giant phase, where the outer layers of the sun will start to extend to potentially just before the orbit of the Earth. But that's quite a violent stage, a stage where Earth probably wouldn't be hospitable at that point. It'll start to go through a very torturous stage where it starts to fight with this ability to continue the fusion process in its core, and that ejects quite a lot of material that can be quite damaging to planets surrounding it. So it can be a less comfortable place probably in the next 4.5 billion years' time. But then after that, it won't really end with any great big firework or anything. It's just the sun will have used up all of the hydrogen in its core and surpassed the ability to be able to fuse hydrogen. It'll surpassed the ability to create to fuse helium together, and moved up to producing carbon in its core. And then after it dies, it'll just leave that big ball of carbon that was in its core behind. I almost think of it as like a very big, hot, non-compressed diamond. So it's kind of in its pre-diamond state. It's super, super warm. And that'll just sit there for a very long period of time, surrounded by these big clouds of gradually expanding gas. So it'll be more of a pff than a kind of thing.
Right, okay. I wondered if it was like it would collapse down on itself and sort of suck everything in from around it. It's not going to do that.
Nah, sadly not. No, sadly not. No, slightly less dramatic than that. Big stars, they have the potential to do something similar to that. Although they're less likely to suck in stuff from around it. More that the star would collapse in on itself, and then anything that was surrounding it when it had collapsed in on itself would be propelled and ejected away from the star as it explodes into a supernova of some description. But there is one process that actually stars like ours can go through, which can create a huge cataclysmic explosion. And I kind of digress when I talk about this, but our sun, if it had a neighbouring star, which many of the stars across our night sky do, we often find stars lesser in their singularities, more in their duets or triplets or quadruplets or sextuplets or whatever it might be. We see stars in lots of different configurations, multiple star systems, very much like Tatooine. But if we had two stars in our solar makeup, so we had our little baby sun and that died and became a white dwarf, which is the term that we give those stars, which are just a tiny little carbon ball left over. And then its neighbour entered the red giant phase, where it starts to increase in size. That process there that happens may start to the little white dwarf may start to hoover material from the dying red giant star, almost like a little zombie or vampire. It starts to hoover the outer layers of the neighbouring sun. And then it reaches a very, very precise mass that it's hoovered from its next door neighbour. And when it reaches that mass, it's always the same. It blows itself up in what we call a Type 1a supernova explosion, which is where the star blows up at precisely the same brightness every time at the same mass. And they're really useful for us because they allow us to measure the distance to very distant places such as galaxies and such like that. So that is one way that our star could blow up if it had a neighbour.
It's sort of fascinating to think that this big ball of fire that we have in our sky every day, and particularly this time of year in the summer, it can beat down and emit all this heat and everything else, that in billions of years from now, it'll effectively just all boil down to be a lump of coal floating in space.
Yeah, essentially.
I think that's kind of a funny thing, that it's sort of like, I don't know, you would expect a more dramatic end to that it just sort of become a little rock that goes plop, that's it. There it is.
Bloop, that's it, done. Yeah, it's anticlimactic end, but it is quite an interesting object. It's a really interesting object. And I think it's interesting that we talk about the heat that we get from it as well, because what's worth considering with all of that is the reason we're able to see it, the reason we're able to feel our sun, is because of those processes that are taking place inside of it. So that stuff that happens in the core, the hydrogen fusion that happens in the core of our sun, is producing that heat, producing the light that allows us to see it. But what's more fascinating about that is the statistics around that. I am a fan of good facts and statistic and nice Earth comparable thing around the statistics as well. So, and what I mean about that is that every second our sun will fuse, and this is my favourite fact. Every second our sun will fuse 600 million tonnes of hydrogen into 596 million tonnes of helium. That's a lot every second that ticks by. For 600 million tonnes of hydrogen to make 596 million tonnes of helium. But you notice there we've lost a little bit of mass. We've lost 4 million tonnes of mass has ceased to exist. It's disappeared. But that cannot happen. That's not how the universe works. You can't lose mass. It's not like losing change down the side of the sofa or whatever, and you generally tend to find that anywhere. And in this case, you kind of do. You find this 4 million tonnes of mass. It's just not that mass that you might have recognised previously. Instead, it's become energy. And the energy output of our sun is astonishing. I'll give you the actual figure is 3.82 times 10 to the 26 joules per second, which is a nonsensical figure and a really, really big one. But to give you some context in that, if you take 1 second of sun energy, so that 3.82 times 10 to the 26 joules per second, and you convert it to Earth energy as if you were to use it here on Earth, that would keep our planet running for about 1 million years. From 1 second of sun energy. And of course, we get to feel some of that energy through heat, the thermal energy. We get to see it through light, albeit that light originates quite some time ago. So the processes that are taking place in our sun that create that light, that has usually happened maybe 200,000 years before the light leaves the surface of our sun and then takes the journey to Earth, which takes 8.5 minutes at the speed of light. So when we see the sun, we're looking back in time by 8.5 minutes, which is the defining principle of the speed of light, and using that to translate to distances.
Yeah, absolutely. That's a good fact that about them. And what's 1 second of energy coming from the sun would power our Earth entirely for 1 million years.
Yeah, something like that.
So we need to
imagine the cost of energy.
I was going to say, I mean, where we're living in the world at this moment in time, of course, things are not cheap. I'm just wondering, maybe NASA's next mission should be just to float a giant, huge solar panel and a massive extension lead back to Earth and just, harvest that energy just for 1 second. That's all we need.
The energy debate is really interesting as well, because it doesn't take a great deal to keep our lights on the Earth. We wouldn't need to harness all of that. We could harness just a good amount of light on a lot of solar panels over a very small period, over a small patch of land. So if you got a patch of land in Africa and you stuck a whole heap of solar panels on it, not very big, only a few miles wide by a few miles, about a few miles wide in each direction. You wouldn't need a great deal of solar panels to fuel our entire planet. The difficulty is, of course, first off, who pays for that and who makes money from that? But that's a totally different debate entirely.
So the answer is very much staring at us in the form of the sun.
Yeah, for sure, or just fusion. And this is a really exciting part of science now. Really, is a very heavily researched part of science right now, is to try and recreate the conditions of fusion here on Earth. Because if you can make a fusion reactor, then you can create an infinite power source for our planet. And creating a fusion reactor, again, sounds really nice and simple in principle. We're taking elements, smashing them together to create heavier ones. But that's not easy. That's really not easy at all. Because at the moment, the fundamental issue that we have is that we need to give an engine more energy than it outputs in terms of creating fusion in that way. However, there has been some really good leaps in research in that recently. And France and China are currently leading the way on this research. And eventually, I think it will be a possibility that we end up with hydrogen fusion reactors. Here in the UK, there's a factory or a facility which is being constructed, which is being funded quite heavily by Jeff Bezos. So your Amazon monies are going towards hydrogen fusion in some way.
Yeah, so we've seen about that, and the hydrogen fusion reactor is one thing, and then similarly harvesting the sun's rays in sort of more conventional manner through solar panels. And I think Elon Musk's on that, isn't he? And he's got big farms there and trying to harvest all this energy into a big sort of warehouse full of batteries. Then again, that will be enough to power a lot of stuff for quite a long time.
Yeah, that's it. If you can create a surface area large enough to capture sunlight on and reliably, then yeah, you can power a great deal of things for a long period of time. The Metro Centre at the moment is constructing a solar panel roof of some description, a canopy which powers some electric vehicle chargers underneath, and part of the Metro Centre as well. So it's a really effective way of capturing light and converting it to a sustainable source of energy. Just need lots of people to do it. The problem is that it's very expensive and it isn't the most efficient way of doing it right now. But technology is creeping forward and has been for quite some years. So maybe 10 years, 20 years' time, that is the most sustainable source of energy, is to have a whole roof of solar panels or whatever it might be. The answer is the sun, everybody. That's the conclusion of today's episode. Thanks for listening. No.
That's pretty much the message, yeah. And then on the subject of other stars as well, we were talking about Canis Majoris earlier, which is a star that's dying, but similarly, it has been discovered that by the Very Large Array Sky Survey, the VLAS, a 7-year project to create a radio map of the sky. In scanning the sky, they have discovered a new neutron star, which is in a dwarf galaxy about 400 million light years away. Now, it was first seen in 2018, but they started doing the survey in 1998. But when they first started doing the survey, it wasn't there. And they've gone back round and scanned the night sky again, and then they've discovered this new neutron star is there. So they think that this star could be as young as 14 years old, maybe slightly older, maybe just old enough to join the army. We're not quite sure yet, but it's relatively new. And of course, it's fairly rare to find new stars. There've been other stars obviously spotted, but not necessarily of this intensity. Now, the radio energy, because this has been discovered by the radio telescope, the radio energy from the star known as, are you ready for this, the catchy name of VT 1137-0337, is 10,000 times more powerful than that of the Crab Nebula. Now, if you're listening to one of our previous episodes, we had a good chat about the Crab Nebula, the one where we were talking to New Zealand. We were talking about the Crab Nebula there. And that was created by a supernova in 1054 AD, so nearly 1,000 years ago now, whereas this one is just as young as 14 years. So reasonably rare to find something potentially this bright, and they reckon that this could be on its way up. It's come from another supernova and could be increasing in intensity as we go.
It's really interesting that as well, because this is very, very far away. 400 million light years away, isn't it, or something ridiculous? So really, really, really distant. Seeing a star at that distance is just impossible. But being able to detect radio signals such as this is very achievable using really high resolution radio telescopes such as the VLA, and interesting that it should be the VLA as well, because that is the site of the workplace of Jodie Foster in the 1997 film Contact that I mentioned previously, where she was sat listening to the sounds with the headphones on. So it's a beautiful site. I think there's 48 ginormous radio antenna, and radio antenna, they work much better when you connect them together, because that's what gives you a higher resolution, and that's the kind of benefit of using those against being able to use visible telescopes like that. It's a bit strange, but using radio telescopes like that, you can do, and that gives you really great resolution. So amazing that they've been able to spot this, and they're fascinating things in neutron stars and nebulas such as these planetary nebulas, as they sit into the category of. Because this is the stuff which ultimately will go on to create all of those heavy, dense elements that we need to create planetary systems such as what we've got here in our solar system. All of the really heavy, dense materials comes as a result of the collision of neutron stars. So if you get two neutron stars that end up gravitationally bound to each other and spiral round each other to the point where they eventually meet and join together, that process of fusion that starts at that point where the two collide is what gives you all of those heavy elements, such as things like osmium, iridium, gold, platinum, uranium, all of that interesting, cool stuff that gives us other stuff in the periodic table. And I think this is actually something worth mentioning at this point, because we're mentioning about that right now, is that the job of a star is to ultimately produce elements in the periodic table. This is where our elements come from. So whenever you hear about, we're made of stardust, yes, we are. We're made of stuff which has formed from stars previously in our universe, whether that be through the simplistic scenario of a star blowing up or the process of two stars colliding with each other. That's what creates everything in our universe. That's what creates everything beyond hydrogen and helium and a little bit of other bits and pieces that were lingering around in the early stages of the universe. All of that comes from stars.
And one final thing to mention, and as you touched on it, was another story I saw, but its roots are not a million miles away from Kielder by any stretch of the imagination, in that an international team of astronomers have combined the power of 64 radio telescope dishes for the first time, and they're using this to detect the faint signatures of natural hydrogen gas across the cosmological scales. And this is all part of the Kielder Observatory system, which has got its headquarters at Jodrell Bank, of course, but they're pulling together the radio telescopes from around the world, 64 of them together, to give a huge map of maybe the makeup of the universe.
And that'll be astonishing. I mean, being able to see in that resolution is outstanding. The square kilometre array, or the SKA, it's the surface area that they're achieving there in terms of resolution. That should give us a really great resolution view of the universe. And what's interesting, and I should probably point this out at this point, is when we're talking about radio waves, we're talking about light here as well. This is still light. It's still within what we call the electromagnetic spectrum. Radio signals are light. They're just very, very long wavelengths of light. Now, light travels in two different ways. We've got a particle, or maybe not best to use that word for it, but we've got a photon, which, if you want to think of that as a physical thing, it is. And then you've got it functioning like a wave as well. And the length of that wave is what dictates its colour. So in our human terms, we can see everything through red to violet. and everything in between. So that entire range of the rainbow, if you like, we can see all of those colours. But we cannot see outside of that. There is something which is, as you may term it, redder than red, which will be infrared, and then down to microwaves, and then down to radio waves. They're very long wavelengths. And then we've got the stuff on the other side, which is shorter wavelengths, so bluer than or more violet than the violet stuff, ultraviolet, and then into X-ray and up to gamma radiation. Now, the stuff that sits off the violet side, that tends to hurt us as humans. But the stuff that sits off the red side is the stuff that doesn't really hurt us. Radio waves and microwaves and infrared, all of that stuff is very undamaging to humans. It doesn't hurt us at all. With the caveat that you shouldn't stick your head in a microwave oven, because that doesn't end well. But they don't tend to hurt us. So that's safe radiation. And you'll notice that the violet stuff is very, very dangerous, the stuff off the violet side. And that's interesting, because then that shows you that stuff becomes more energetic as the wavelengths get shorter. And then when we're talking about things like star colour, when you look at a red star, it's much cooler than a blue star, and it's because the red star's much lesser energetic than the blue one. The blue one's much, much hotter. Don't know how I ended up talking about that. I just took that little detour there.
Yeah, well, the big takeaway there is, if you're looking to get an idea of how the universe formed, don't put your head in a microwave because it won't give you the same results. Wise advice there, and I think that that brings us nicely full circle, really, on the stars. Obviously, there's lots more you can learn about stars, and you have some specific sessions, don't you, from time to time at Kielder about the secret life of stars in the universe?
We do. We only just touched on a few different factors when we were talking just there. We talked about a little bit of formation. We talked a little bit about the end point as well, the death. And really, to connect all of those dots, we run an event called The Secret Lives of Stars, which tells us all about the evolution and death of stars. And that's the one that I would recommend if you want to learn a little bit more about the life cycle of stars, which is a very fascinating topic. And it's certainly the one that I would recommend that you visit before you go on to the harder topics, such as origins of the universe, which takes all of that information that we've learnt about stars and then expands that out to the greater universe to help us understand a picture of how we understand the age of our universe, where it came from, and ultimately where it may end up as well.
Yeah, the universe is really mind-boggling to get into as you get deeper into it, if it's not something you've really touched on. Even just some of the discussions we've had on this podcast over the time with various experts, it just scrambles your mind to think of some of the things that may be possible or may be out there. It's it's a big old subject, so definitely find out more about it, and come and visit us at Kielder Observatory. Plenty of sessions available over the coming months, so pick one of a subject that you fancy. You may want to take in that one about the secret life of stars. I'm just looking to when that might next be on, if it's happening anytime soon. The Secret Life of Stars, yes, and there's currently, at the time of recording, spaces available. The 16th of July is the next time that's going to be happening on a weekend. So that's one, and then it's going to be the week after on the Sunday. So there's a few of them, actually. There's loads. If you're into your stars, so a few in July, and then of course more in August and September, October, and as the year goes on, pick a date that's good for you and see all the other sessions available over the coming months. And of course, for the 6 weeks holidays, get booked in now online, kielderobservatory.org. Well, that does nicely, I think, for this month's episode of the Kielder Observatory podcast. We'll be back in the next month, and we'll be able to update you on what's been happening through July, and then starting to take a look at August. Of course, the night starting slowly by then to get a little bit darker, and more things heading into the night sky as we go into the end of summer and into the start of autumn, and we might just be heading into prime aurora time as well, might we, around then, Dan?
Ooh, that's exciting, isn't it? Yes, quite an active year this year as well. So we've seen so far. So maybe when we get into autumn, we'll see some really good auroras Fingers crossed.
Fingers crossed, you never know. Okay, well, enjoy your stargazing, and of course keep up to date with everything happening both on the website and on the social media pages of Kielder Observatory. Just search for Kielder Observatory on Instagram, Facebook and Twitter, and you find out all the latest info and any short notice availability as well, because from time to time people can't make it and they're very kind enough to let us know, and we can offer those places at short notice sometimes, so you never know. Places may come up if indeed your chosen date is not available at this moment in time. Have a listen to some of our previous episodes as well, including volcanoes of the solar system and how the moon used to have its own raging lava all over it. Dr. Natalie Starkey joined us on that episode to talk about that. We also spoke with Dr. Olivia Jones, part of the mission behind the James Webb Telescope, which we're going to start seeing some images of fairly soon, I think, a lot more. So she was talking about the launch of that, but there's also the obviously it's since launched, but some of the things that we can expect to see of it over the coming months and indeed years. And we were also speaking about the Royal Astronomical Society recently as well, with Dr. Robert Massey, who's the Deputy Executive Director of the RAS, talking about their 200 years and counting of looking after the night sky in this country. And in the previous episode, we were talking about the things that you can look out for through the course of the summer months as well, not least noctilucent clouds, which is one of Dan Pye's favourites, and they're visible over the next few weeks and months or so as well. So that draws us to a close of this month's episode of the Kielder Observatory podcast, and we'll speak to you next time. Take care. See you later.